Welcome to Math341, Lecture 11. What we're going to do today is we're going to continue our conversations about continuous and discrete random variables, and we are going to start talking about expectation. We will look at some of the technical details and difficulties that arise. In particular, we will look at one of my favorite distributions, the Cauchy distribution. Out of curiosity, how many of you have looked at the Cauchy distribution before? Okay, not too many. It should become on your list of go-to distributions when you need something bad. Okay? It's nice to have distributions where things aren't nice. Because if you keep looking at things that are nice, you sometimes are misled as to what's going on. So in Chapter 7 and Chapter 8, we talked about continuous and discrete random variables. We talked about why we like continuous random variables more. What was the big thing that helps us with continuous random variables?
Integration.
I'm sorry? Integration, and the fundamental theorem of calculus that the area under the curve corresponds to the antiderivative at b minus the antiderivative at a. We just tend to have better formulas for integrals than we do for sums. This doesn't mean any integral is better than any sum. There are some sums we can do while some integrals we can't do, but a lot of the nice standard functions have nice expressions for their integrals. So we have something called the CDF, the cumulative distribution function. And as always, we want to use good notation. So x will be a random variable. I will often either assume x is discrete, continuous, or go back and forth. You could, of course, have random variables that are mixed, that are discrete for some parts and continuous for others. Let's say it has density or PDF little f sub x. So the sub x reminds me which random variable I'm talking about. If it was a discrete distribution, instead of saying the probability density function, we might talk about the mass density function. So we'll say the cumulative distribution function is capital F of x, and this is going to be the probability that x takes on a value less than or equal to x, or the integral from minus infinity to x of fx of t dt. So I have to use a different variable for my dummy variable integration because I want to calculate the probability I take on a value at most x. So if I have some distribution which integrates to 1, it would be the area up to some point here. Okay? So basically, think of it as a running tally of how much probability you have up to and including this point. If you have a continuous random variable, up to and including, they're the same. The probability of one point in a continuous system is 0. In the discrete setting, however, it makes a huge difference. The probability of, at most, a sum of 4 is different than the probability that the sum is less than 4. It differs by the probability of being exactly 4. And in the discrete case, exactly 4 can often have a significant probability. But in the continuous case, the probability of any singleton event will be 0. All right. So the first thing to ask is, what kind of properties does it have? So any thoughts on properties of the CDF? What do we know about it? Yes?
Should always be positive.
Nope. Close, though. You have to modify positive ever so slightly. It should always be no. Well, okay. So combine the non-zero with positive.
Right.
It should always be, how do you phrase it?
Non-zero and positive.
Greater than
Non-negative.
Non-negative. Right? The running tally is never going to be negative, but it could be 0. Maybe I have a random variable that only takes on positive values. I'm looking at how many runs my team scores. It's not going to be a negative number. Yes?
As x goes to negative infinity, CDF equals to 0.
Good. So the limit as x goes to negative infinity of the cumulative distribution function should be 0. And related to that will be as x goes to infinity, it should be
1.
yes.
It should be either flat or increasing at every point.
Good. So the nice phrase is non-decreasing. Non is a great adjective or prefix or whatever you want to call it. Prefix, I guess. Non is a great prefix to put on top of words. It's non-negative. It's non-decreasing. You know, the probability, the running tally doesn't somehow drop down as you go further up. If you know the cumulative distribution function, do you think you know the probability density function? Do you think you can recover it? What do you think? We have two questions. Does the CDF imply the PDF? And does the PDF imply the CDF? Which one of these questions is easier to answer? First or the second? The second. If we know the PDF, well, the CDF is defined as the integral, so this one is clearly a yes. The first one is a little harder. If you know the CDF, can you calculate the PDF?
We take the derivative.
Okay, so we know, fx of x is the integral from minus infinity to x of fx of t dt. The goal is to use good notation. I hop on this all the time. You want to be able to look down and see what is going on. And because I have a capital F and a little f, you should be thinking there is a relationship between them. This is why we use big F and little f in calculus. So that whenever you see the big F, you should be thinking, its derivative is little f. So, by one of the versions of the fundamental theorem of calculus, do we then get that if we take the derivative of this, we just get little fx at x. Is that true? The answer is mostly. What class do you think is useful here to make things rigorous? When in doubt, what class do we use to make things rigorous? Real analysis. So a lot of this class is going to be a justification for why you should suffer through real analysis. Or if you're not going to suffer through real analysis, why others have suffered through it for you. Okay? You need to be able to justify. Well, if I make my function f of x equals, say 2x, 0 less than equal to x, less than equal to 1, and 0 otherwise. Is this a probability density function? Non-negative integrates to 1. What is big? So what will big f of x be? I think it's just x squared if 0 is less than equal to x is less than equal to 1, and 0 otherwise. Whoops, no, 0 if x is less than equal to 0, and then 1 if x is greater than equal to 1.
No.
I'm sorry? Did I make a mistake?
No.
Okay. So I can calculate the cumulative distribution function. If I take the derivative, I get my original function. If you look at your function, 2x, I should be able to plot this. Here's 0, here's 1, here's 2. Here's my function. If at the point 1/2, I change the value of the function and make it 0 at 1/2, and I change the density, is that going to change the calculation of any of the areas? No. Is it going to change what the CDF is? No. But it will change what the PDF is at that one point. So this is the technical thing you have to be a little bit careful of. If you know the cumulative distribution function, you can get information about the derivative in real analysis or measure theory we say almost everywhere. There can be a couple of bad points, and there can even be uncountably many of them, but they can't have much measure where things can go wrong. And there are techniques you can develop. Now, if your initial densities are nice and continuous and differentiable, then all this vanishes. You know, we have a discontinuity here. We have a change in definition at one point. When you look at this as your PDF, would you ever want to use this as your PDF? No. You would immediately redefine it to be continuous and differentiable, because it won't change your probabilities for any events. And at the end of the day, that's what we care about. We care about calculating probabilities. So I could give you this, but I'd never use it.
When does the lack of continuity become a problem? Because at one point it's not a problem.
It's going to be over a set with measure, a set with length.
Okay.
And so if you have uncountably many points like this, it could cause trouble. If you have only countably many points, you should be okay. Just as a rough rule. Yes?
So does that mean the differentiable is an assumption for?
Well, if you assume your probability density function is differentiable, then this can't happen. And then you can recover. So this comes down to how much rigor did your professors have when they proved the fundamental theorem of calculus? My feeling is little, if it was even that high. And you just have to be careful. If your function here is nice, then yes, you can differentiate under the integral sign, and you can get that the derivative of big F is little f. But this is one of the reasons why we love cumulative distribution functions so much. And if you go back to the discrete case, if you want to calculate the probability of exactly, so we'll do discrete. So probability that x is exactly equal to k is the probability that x is less than equal to k plus 1 minus the probability that x is less than equal to k. So if we use the following, we can go from these inequalities to equalities. And in the discrete case, you can have and often will have a positive probability of being exactly k. So if we can calculate the cumulative distribution function by looking at the difference, we can then get exactly. And this is a common technique. This is a common trick. It's used in many, many problems. Right. Any questions about the beginning, about these properties of the cumulative distribution function? Right. So at this point, we're essentially done with chapters 7 and 8. So now we're moving on to chapter 9, which is expectation. All right. So now we're going to begin to start to apply the stuff. Out of curiosity, how many people here have taken at least Stat 2 or 1 or its equivalent? All right, how many people have not? Almost every hand, I think, went up for one or the other. Okay. So what I want to do now is I want to talk about expectation. And again, a lot of what we're doing is we want to find good notation so that we can glance down and see what's going on. So I'm going to risk trying to recall something from Calc 3 or from linear algebra. Have you seen either of these expressions? Okay, what do they mean? Magnitude of the vector v. How many of you use the double lines? How many use the single lines? Eventually you move to the single lines and you overload the notion of the absolute value. I mean, when we first learned the absolute value, we learned the absolute value of a number. You can extend it and now have the absolute value on a vector. If I have the arrow over v, I'm not going to be that worried that I will forget that v is a vector. If I don't have the arrow, I could forget that it's a vector. When you write the double lines like this, it's really clear what's going on. That this is, not the standard absolute value, it's some kind of generalization, but it's more work. And eventually we just start abusing notation and we start to say, So similarly here, I'm often going to write things just for the continuous random variables. I'm not going to do things for the discrete random variables. The calculation is very similar. There's a way of defining the general integral sign where the general integral sign could actually be the same as the discrete sum. And it's just a more unified language approach. All right? If not, just as good exercise to take everything I'm doing and then just rewrite it. If I did the continuous case, do the discrete. If I did the discrete case, do the continuous. So we're going to use, this is called Blackboard E. It's meant to remind you that something special. The expectation of some function of a random variable x is equal to the integral from minus infinity to infinity of g of x f x of x dx. So this is my definition of the expectation of g of x, where x is a nice random variable with density f of x. So the nice thing is we've done this so many times now, I don't have to waste chalk or waste class time by saying x is a random variable with density f sub x. That's now just part of our notation. Different choices of g will lead to different quantities. Some quantities are worth studying, others are not. If I give you an integral, what's the first thing you would like to know about the integral?
It's range and where from which 2 points.
Well, so I'm telling you it's minus infinity to infinity. Does it exist? Right? Maybe this integral is undefined. If the integral is, if you're lucky enough that the integral exists, what's the next thing you'd like to know? Once you know it exists, you might want to know its the area, you might want to know its value, right? So can I actually compute the value? So now the question is, for which times can I do it? So for example, let's say I give you the integral from negative infinity to infinity of e to the negative x squared over x to the 4th plus 100 dx. I am not asking you to compute this integral. I'm just asking you, does this integral exist? Is it finite? What do you think? I'm saying heads nod. It's always non-negative. Denominator is never 0. In fact, the numerator is always at most 1, and the numerator is decaying very rapidly. The denominator is also decaying very rapidly. It has wonderful decay in both directions. So there is no issues with this integral converging because we have such rapid decay. Right. For other things, it becomes a lot harder. If I give you, the integral from 0 to infinity of x to the a dx. Where are the two problem points in analyzing this? I'm sorry?
The value of
Right, so I'm saying I want to figure out for which values of a, if any, is this integral finite. Where do I have to worry about the integrand?
When a is equal to -1.
Well, I'm saying that's for specific values of a. Where are the potential problem points for the integrand? I'm sorry?
It could be infinity or undefined or division by 0.
Right, so where could I have division by 0?
It's -0.
Well, my integral is going from 0 to infinity. Which, yes? Well, that's specific values of a. I'm saying which values of x do I need to worry about? 0. So I need to worry about what's going on near x equals 0, and I need to worry about what's going on as x goes to infinity. So we would want to say that this is x to the a plus 1 over a plus 1 evaluated at 0 and infinity. If I want this to be converging at infinity, what must be true about a? Yes. A has to be less than what?
1.
Not 1. Not 0. -1. I need x to the a plus 1 to be going to 0 at infinity. So if a is not less than -1, if a is -1 or greater, I'm going to have either x to the 0 or x to a positive. Well, if a equals -1, maybe I'm okay. Because that would be x to the 0, which is 1. Turns out I'm not, that's a logarithm. We need a to be less than -1. What about over here when x is near 0? What do I need to make sure that this is okay? What must be true about a for this to be okay? Yes. So if A is 0, if A is 0, is everything fine near x equals 0? Yeah, I'm just integrating the function 1. So if A is 0, everything is fine. I don't want this to blow up too much. I'm sorry? So if A was 2, 3, 4, if A is positive, everything is fine. What if A is negative a half? What's the integral of x to the negative a half? That would be x to the 1/2 over 1/2. That would be fine. So what's the critical threshold for A? If A is -2, I have the integral of 1 over x squared. When I integrate that, I'm going to get something like 1 over x. That's going to blow up. I need A to be greater than -1. Whoops. Okay? There's no way to fix this. One side is pulling me to have A less than -1. The other side is pulling me to have A greater than -1. I can't make this a probability distribution. There's no way to normalize it. The integral is fundamentally infinity. What I can do is I can change either the lower or the upper bound of integration. If I start at 1, then this is no longer an issue. If I don't go to infinity, then this is no longer an issue. And you can use that to then fix your distribution. But you need to get into this habit of when you get a function, you want to get a feeling of when is this integrable, what are the values, what are the danger points, where am I dividing by 0, where could I possibly have an infinity? Okay, any question about this? All right, so this is an example. Let's go back to G. What do you think the easiest choice of G would be? Easiest choice, yes.
G of x equals x.
Nope, that's the second easiest. 1 or any constant. 0 is a special constant. I will actually say the constant is almost as easy as 0. I agree that g of x equals 0 is technically a little bit easier, but if g of x is always a constant, c, then we get the integral from -infinity to infinity of c times fx of x dx, which is just c times the integral from -infinity to infinity. And what do we know this integral equals? 1. This is a no-shocker, right? If g is identically c, its expected value is c. So think of expected value as the average. But it's an average where every point is not weighed equally. We use the density f of x to weigh things. So for instance, maybe I have something like this. Freshman year, sophomore year, junior year, senior year. We're doing a GPA, and we're going to weight your GPA, so now all classes aren't equal. They are weighted by what year you were when you took them. Or maybe we weigh them by a 100, 200, 300, 400. Getting an A in a 400 level class is worth more than getting an A in a 100 level class. So there are lots of times when you would want to have unequal weightings. Okay? Most of the time, if you are comparing yourselves to your peers, you will do equal weightings. What's the average grade in the class? What's the fluctuations? Freshman grades count the same as sophomore grades, count the same as junior as senior grades here. There are other schools that feel very differently. And there are schools where freshman grades don't count. And they're mandatory pass-fail. So the whole point of f of x is it's putting on a bias. And then this gives you the value, the average value of g of x subject to this bias. Well, if g of x is always constant, then this is not a problem. We're going to just get that constant value back. Then the next thing to look at, as was suggested, is g of x equals c. That's a really good thing to look at, and that's going to lead to what's called the average value or the expected value. And so we will use the Greek letter mu to denote the average value. And for many things, this is the most important value we get. So mu is the mean, it's the expected value of x. So this is taking the special case where g of x is just x. Okay. The next thing we can look at is the nth moment is going to be the integral from minus infinity to infinity, x to the n, fx of x dx. So here we're taking g of x is x to the n. So if you want, you can think of these as very simple functions to look at. 1, x squared, x cubed, x to the fourth, x to the fifth. You could use more complicated functions, and the idea is I want to understand my density function f of x. I know these moments for different choices of n. What can I deduce of my function f of x given my knowledge of the moments? So we want to use moments to understand f. And in fact, this is how we will prove the big result of the course, the central limit theorem, by using knowledge of moments to get something about f of x. It's incomplete information, at least in the case when f is continuous. But the hope is that if we know enough of the moments, then we know the distribution, that there should only be one distribution that has this as its string of moments. Unfortunately, we know whether or not this is true. We talked about this in the last class. Is a function uniquely determined by its Taylor series? No. So recall Taylor series are not unique. Consider the function e to the negative x squared. 1 over x squared. Because of terrible functions like this, probability is difficult. What we really need is not the moments when n is an integer. We need the moments when n is a real number. And then what's better than real analysis? When real analysis is not enough, what do you go to?
Abstract.
No, not abstract, never abstract. I've never even taken abstract.
Complex.
Complex, right? When real analysis fails, you go to complex, because complex is the country club of mathematics. It does not let all functions in. Real analysis will let functions like this in, and real analysis will allow a function like this to be differentiable. If you let z equal x plus iy, every now and then a Williams math major graduates without knowing the square root of -1 is I. That never happens with me. So you've at least now seen at one point in your career the square root of -1. If you let z as x plus iy as a complex number, the function e to the -1 over z squared, the complexification, that is a word, of e to the -1 over x squared is not differentiable. It's not even continuous. Complex analysis is very different. To be differentiable in complex analysis is a huge condition. And it turns out that differentiable functions in complex analysis have properties that they don't have in real analysis. One of them is if you're differentiable once, you are differentiable infinitely often in complex analysis. That is not the case in real. You can have terrible functions like x cubed sine 1 over x, where that function is differentiable once but not twice. In complex analysis, if you are differentiable once, not only are you infinitely differentiable, but you equal your Taylor series, which converges to you in a non-trivial region. There's so much more that is true. And it turns out, if you understand the moments, not just when n is restricted to an integer, but when n goes in a continuum, or you can do a little bit weaker than that if you know points of accumulation, but when you have a huge amount of moments, then you can deduce uniquely what you must have. And that's the problem, is that knowing a discrete set of moments is not enough. It's because of Taylor series like this that we have trouble. And again, I'm not going to go into all the details of that in this class, but I want you to at least be aware of what are the challenges, what are the difficulties, what do we need to take care of. All right. So unfortunately, while we hope that knowing the moments will determine the function, it's not always the case. It sometimes is. One of the things you also learn is sometimes the first quantity you look at is not actually the easiest one to study. You might notice that there's a prime here. The reason that there's a prime is because this is not the nice object we like to study. We often study mu n, which is the expected value of x minus mu to the n. And just writing this out, it would be the integral from minus infinity to infinity of x minus mu the n density fx of x dx. So this is the nth centered moment. One of these centered moments should be well known to you if you've taken Stat 201, which is the well-known centered moment. The variance. So the variance, sigma squared, is just mu2. And that'd just be the expected value of x minus mu squared. It's how spread out are you from the mean. Okay? So what we're basically doing is, if the mean is finite, then we might as well just adjust things and look at the fluctuations, but we're just changing our scale. We're just changing our 0 point. All right. So for the rest of the class, I want to talk about the Cauchy distribution. So the Cauchy distribution is one of my absolute favorites. So I'm going to start off with f of x is 1 over 1 plus x squared. What do you think about this being a probability distribution? Yay or nay? And if the answer is nay, how badly nay? What does it have in favor of it?
Because x squared is always positive, we don't run into divide by 0 errors, and we won't be really.
Good, we're not going to run into dividing by 0 errors. It's also non-negative. And if I integrate from minus infinity to infinity, I have enough decay with the x squared that I'm fine. And because I have the plus 1, I don't have to worry about having a 1 over x squared at the origin. So this is actually integrable. What do I need if I want this to be a probability distribution? Yes?
The area to sum to 1.
Yeah, the area has to be 1. Given how I've written it, do you think the area is 1? No. In an act of incredible foresight and foreshadowing, there was enough space left to draw 1 over pi. So the area under this function is pi, so if we multiply by 1 over pi, we now have area 1. This is a wonderful function. So I first want to talk about why this is true. So how many of you remember the derivative of arctangent is 1 over 1 plus x squared? Okay. Let's start with the arctangent function. If you could choose any function in the world and evaluate that function at arctangent, what function would you like to evaluate at arctangent? Tangent. Arctangent of x means the angle whose tangent is x. I will take the tangent of the angle whose tangent is x. And in a Straka, the tangent of the angle whose tangent is x is x. We can use this to get a derivative for arctangent. So if f of g of x equals x, by the chain rule we get f prime of g of x times g prime of x is 1, which means g prime of x is 1 over f prime of g of x. So we can get a derivative of the inside. So this tells us that arctangent prime of x is 1 over tangent prime at arctangent of x. Okay. So we have a formula for arctangent. It is a correct formula. It is not a pleasant formula. Right? I'm claiming it's 1 over 1 plus x squared. 1 over 1 plus x squared, I can work with that without too much trouble. 1 over tangent prime of arctangent of x, I can't work with that as well. All right? Let's draw a triangle. I have some angle here, and I want to draw a right triangle such that the tangent of this angle is x. What should I have for the lengths of my sides? So I want to draw a triangle such that the tangent of this angle, yes?
X is 1.
Yeah, which one is x?
The opposite one.
The opposite one, yeah. So if this is x, this is 1, what's the hypotenuse? Square root of 1 plus x squared by Pythagoras. If anybody wants, I just gave a lecture in 331 today on how to prove Pythagoras and how to sniff it out. So now that we know this, we can actually calculate tangent very easily. This angle here is the arctangent of x. So now, the first thing we need to do is, what's the derivative of tangent? So tangent prime of u, anybody remember the derivative of tangent? Sine of u over cosine of u, and take the prime. So when the dust settles, yes, it's 1 over cosine squared, which is the same as secant squared of u. If you forget this, you can either look it up or even better, just use the quotient rule. And then you get the derivative of tangent is 1 over cosine. Okay, well, this tells me I want to calculate the cosine of this angle. So the cosine of arctangent of x is just going to be, the cosine is 1 over the square root of 1 plus x squared. So then 1 over the cosine squared of arctangent of x is just 1 plus x squared, which is just arctangent prime of x. And there's our proof that the derivative of arctangent is, whoops, I must have made a mistake somewhere. So the arctangent is, well, which 1 over the derivative of that, thank you. So it's 1 divided by all of that. There you go. And math is consistent again. Excellent. So we get the derivative of arctangent is just 1 plus x squared inverse. All right. So now we can actually use this to calculate the area. So now, if we integrate from negative infinity to infinity of 1 over 1 plus x squared dx, well, by symmetry, this is twice the integral from 0 to infinity of 1 over 1 plus x squared dx. This is twice the integral from 0 to infinity arctangent prime of x dx. I am writing this to make the integration as easy as possible. I'm integrating the function whose derivative is arctangent. So I'll just get arctangent at infinity minus arctangent at 0. All right. What angle has a tangent of infinity? Pi over 2. If you draw your circle right over here at pi over 2, you're going to have no base, all height. So we get 2 times pi over 2, and the arctangent of 0, now my height is 0, the base is 1, that's going to be 0. And so we get that the area under the curve is just pi. So we can convert 1 divided by 1 plus x squared into a probability distribution. We just multiply by 1 over pi. It turns out, if you replace the x squared with x to the 4th or x to the 6th or x to the 8th, you can always convert this to a probability distribution, and you'll always get a nice constant. If you make it an odd number, do you think we can make it into a probability distribution with an odd? Okay, you're shaking your head in horror disgust. Why not? So we did 1 over 1 plus x cubed. What would be the problem? Similar. It's close to canceling out.
Sometimes negative.
Yeah, it's sometimes negative. Once x is less than -1, it's going to be a negative number. But if we just restrict it to x greater than or equal to 0, we could put odd numbers in as well, and it would still be a nice constant. So we are actually fortunate that we can always get nice normalization constants. So how many of you remember freshman year when you meet somebody, there's essentially 5 questions you always ask? Maybe you change up the order a little bit, but there's a standard set of questions you ask when you meet someone for the first time. When you meet a probability distribution, there's a couple of standard questions you should ask. What's the first question you should ask a probability distribution? No, because it's once you're told that you're meeting a probability distribution, you know it's non-negative. I mean, if you're meeting just a general function, you might want to slowly sniff out, is it a probability distribution? Do you happen to be non-negative? What's the first question you would want to ask a probability distribution? I'm sorry?
The sum of the one.
Again, it's a probability distribution, so it has to sum to 1.
I'm
Right?
sorry.
This is I'm not really sure if I can admit to you that I'm a probability distribution, so I want to see if you're a probability distribution. I'm going to start slowly asking some things. What would you like to say? What's the first thing you'd like to know about the distribution?
Do they have a name?
That's a little bit much to ask immediately. What's a lower thing you could ask? Yeah, what's your mean? Do you have a mean? And so the first question is, does this distribution have a mean? So let's try to calculate the expected value of x, which is the integral from minus infinity to infinity of x over 1 plus x squared dx. Where you might think, what should this integral be? What should this integral be? I'm integrating an odd function over a symmetric region. It should be 0. Unfortunately, you have to be very careful about infinities. So it's actually not a bad thing that we start off with a clip from Cam. Whenever you have infinities, you must be careful. I want the integral of the absolute value to be finite. And then if the integral of the absolute value is finite, then we can talk about what happens without the absolute value sign. Now, for this one, it is symmetric. And if you view this as the limit as a goes to infinity of the integral from minus a to a of x over 1 plus x squared dx, you will get 0. But if I look at it as the limit as a goes to infinity of the integral from minus a to twice a of x over 1 plus x squared dx, I'm not going to get the same thing. It matters how I get to infinity. And now when I do this, the integral from minus a to 0 cancels the integral from 0 to a. And this is just left with the integral from a to 2a of x over 1 plus x squared dx. Well, if a is really large, x over 1 plus x squared is approximately what? For x large, x over 1 plus x squared is approximately what?
0.
No. That's a little bit better than 0. Yeah, it's about 1 over x. So this integral is approximately the limit as a goes to infinity, the integral from a to 2a of 1 over x dx. That'll be the natural log of 2a minus the natural log of a. What's the natural log of 2a minus the natural log of a? Natural log of 2. And so you get the log of 2. So unfortunately, depending on how you go to infinity, you can get different answers for the Cauchy distribution. So the question of what does its mean is undefined. Yes?
Can you explain how another x got in the numerator?
I'm calculating the mean. I'm calculating the expected value. I should technically have a 1 over pi. I apologize. I'll put in the 1 over pi's. But so I'm calculating the expected value. And the whole point of this is that not every distribution has a mean. And it's really changed because the Cauchy distribution is symmetric. So a lot of people basically say, screw this, it's got a mean of 0. You can talk about the median. The median is the point where half of your probability is before and half your probability is after. In this distribution, it has a median of 0. And for median, we'll write it here as mu tilde, and it equals 0 for the quotient. Okay? So for a lot of problems, the median is a better thing to study because the median will either always exist or it might exist in a range. If my distribution has valleys where there's 0 probability, you could actually have multiple values being the median because you can shift over and you're not changing any of the probability. But the median will always exist when the mean does not. So for those of you who are actually going to go out on the board and use statistics, it's something to consider. All right. We can have arguments as to whether or not the mean of the Cauchy exists, but at least if we look at the variance of x with the Cauchy, this is going to be the integral from minus infinity to infinity of 1 over pi x squared over 1 plus x squared dx. This is much easier to study. As x gets very, very large, what does this fraction look like? It looks like 1. So this is clearly going to go off to infinity. As a nice exercise, do this rigorously. Say, once x is at least 2, this fraction is at least 1/2. Therefore, this is at least 1 over pi times 1/2 times infinity. So as a nice exercise, make this rigorous. There is no way to give the Cauchy a finite variance. There is no way to give the Cauchy a finite standard deviation, which is the square root of the variance. So we're using sigma squared to be the variance of x. That notation is meant to be highly suggestive. Sigma is the standard deviation. And in Shaka, it's the square root of sigma squared. The Cauchy distribution does not have a finite standard deviation. And a lot of the theorems, like the central limit theorem later in the class, are going to assume we have a distribution with finite standard deviation. Now, there are some theorems that are still true even when you don't have something like this. And it's good to know what can you still have in a situation like the Cauchy. Question?
What are the other questions we asked? Probably.
Well, the first is after you get if it has a mean, then what's your follow-up question? What's your standard deviation? One of my friends was a year behind me in high school and was pre-med at Harvard. And I was visiting her one day, and they were taking a physics class, and they had a list of how people did on the exam. No, they didn't have people's names, they had your ID number. And the professor gave not just the mean and the standard deviation for the class, but also gave the next two moments, the skewness and kurtosis, so that the pre-med students could really compare themselves to fourth order with everyone else. For many things, mean and variance is more than enough. Once you get the mean and the variance, that's typically enough to understand what's going on. But you could ask, what are future moments? You could ask some questions about your rate of decay. You decay rapidly at infinity. You could ask, are you bounded or unbounded? Do you assign probabilities to events that are arbitrarily large? So is it technically possible in a baseball game to score infinitely many runs? Is it technically possible? Yes, it is possible. If the other team can't make outs, you can keep scoring. In soccer, can you score infinitely many goals? No, because it takes a certain amount of time for the ball to travel. Worst case scenario, we use the speed of light as finite. And the rules of soccer, at some point the penalty kicks stop and the game is a tie. In Wimbledon, is it possible for the fifth set to go in favor? Yes. Okay. There are some things that effectively are finite but could be infinite. Could a chess game have infinitely many moves? No, because threefold repetition makes the game stop as a draw. Okay? So one of the big things you might want to ask is your distribution of bounded support or unbounded support? Is it possible to have arbitrarily large values assigned probabilities? That's a really good thing to know about your distribution. Okay, this is a good place to stop.